So in today's lecture, we're going to try to get to the bottom of where these line spectra come from. Last class we looked at fireworks, we looked at that rainbow flame experiment, and we looked at basically that different elements, when they were excited, they gave off a different color of light, and when we broke down that color of light, we realized that the light was actually composed of discrete wavelengths within the visible region. So quick few announcements. The midterm grades will be posted today. Homework grades, I've updated those through Chapter 5. Please let me know. If you missed Chapter 5, I would be more than happy to open it back up for you. I know there was a lot going on. There's a lot of homework and studying for the exam on top of everything else. So please let me know. I can extend that deadline for you. And we need to stay on top of everything because Chapter 6 and 7, they are due this Sunday. We're going to finish Chapter 6 today, and then we're going to look at Chapter 7 Wednesday and Thursday. So one important thing from last class was the two equations that we covered. C equals frequency times wavelength, where C is the speed of light, and energy equals Planck's constant times frequency. And these two equations are very important, and the relationship between these two equations are very important, especially with respect to the visible spectrum of the electromagnetic radiation. So our first equation, C is the speed of light. Right, that's a constant. So frequency and we had wavelength. What is important in this case is their inverse relationship. And what that means is because the speed of light is a constant, right, the product of frequency and wavelength cannot change. That needs to remain constant. That needs to remain the speed of light. So if my frequency increases, my wavelength needs to decrease. So I have an inverse relationship there. Now I need to take that information over here to energy equals Planck's constant times frequency. So here, now my constant is Planck's constant. So now I have a direct relationship because now if I get an increase in frequency, frequency times Planck's constant, that's going to give me an increase in energy. So I have a direct relationship between frequency and energy in this equation. And now if we put these two equations together, which we should be able to do, we should be able to think about what that means, right? Not in the sense of a calculation, but in just a sense of thinking about if I change this, how does it change something else in this reaction? So let's go back to the first equation. The speed of light equals frequency times wavelength. If my wavelength decreases, so if I'm down here, right, in the blue region, I've got a wavelength of 400 nanometers. So I've got a decreasing wavelength. That means I have an increase in frequency. If I increase the frequency, that increases the energy. So that means in this blue region, I have a higher energy, right, than the red region. If I go to the red region, I have a longer wavelength. So I would have an increase in wavelength, which would result in a decrease in frequency. A decrease in frequency going over here would result in a decrease in energy. So we should know, we should be able to think about those two equations, the relationship between wavelength and frequency and energy, to determine approximately the relative energies without a calculation, but just relative energies on the electromagnetic spectrum, thinking of those two equations. So back to what we looked at last class, right? We looked at the flame experiment, and if I burn a sample of lithium, excite a sample of lithium, and put it through a prism, I don't get the entire rainbow, right? I don't get the entire visible spectrum. I get 4 discrete wavelengths of light. I got one in the red, one in the orange, and then 2 in the blue-violet region. And so we kind of talked about last class that there must be some discrete energy levels because with Einstein's work and the photoelectric effect, we decided that energy equals Planck's constant times frequency. Because each of these wavelengths of light has a unique wavelength, right? That means they also have a unique frequency. Well, now I can relate that unique frequency to a unique energy as well. Very important, right? Now we're able to say that those 4 discrete wavelengths of light, they are a product of some energy, right? Some specific energy transition that's occurring within the element. And so that's what we're going to look at today, right? We still left last class kind of unsure of where are these energies coming from. Einstein gave us a good start of helping to understand where that light's coming from. That light's coming from a specific energy transition, but what are those energy transitions that we're talking about? And so the next player in this game was Niels Bohr, who looked at the stability of the hydrogen atom, and he helped work on basically doing something with that line spectrum of the atom and giving us an idea of where that energy could be coming from. So he came up with the energy level postulate, which basically said that electrons must exist with specific energy levels. So electrons must exist within specific energy levels. Where each level is a specific distance from the nucleus. Okay, so we've got these different energy levels that an electron can be found in. Each of these energy levels is a different level from the nucleus, a different distance from the nucleus, and in order for these energy transitions to occur, in order for these electrons to release energy, right, they're releasing energy in the form of a photon of light that we're seeing with our eye. So these electrons must be able to move between these energy levels. Electrons must be able to move between these energy levels. Right? Incredibly important, right? Just putting Einstein's equation back up there, energy equals frequency times Planck's constant, right? Now, that energy we're seeing, right? We're seeing a color of light. That color of light has a specific wavelength and frequency that corresponds to a certain energy. So what's happening is we must have an atom where we have our electron is given energy and it's promoted up to a higher energy state, and then that electron relaxes back down in energy. How does it relax back down in energy? It must release energy equal, right, to that color and wavelength of light that we are observing with our eye, right? That energy corresponds to a photon of light that's given off that we see with our eye. And so here's what that diagram looks like, right? Here's Bohr's theory. Of the atom with that energy level diagram. So here I have my nucleus, right? I have my nucleus and I've got these certain levels, right? Certain stairs, we could think of them, or floors. So n equals 1, n equals 2, n equals 3, right? These are different places the electron could be. And so what Bohr put out was this idea, this energy level idea. Okay, this electron can be at different energy levels, and we excite the element, that electron goes up in energy, right, to these higher energy levels. Well, when that element relaxes back down, it's going to release that energy. It's going to release that energy in the form of a photon of light. And that's what we see here in this hypothetical transition between n equals 3 to n equals 2. The electron falls back down. It also releases energy in the form of red light that we're observing. So that's what Bohr put forth, is that we have these energy levels available that electrons can transition between, and they absorb energy, they go up, and then they need to relax. They're going to release energy to come down. How do they release energy? They release energy by giving off a photon of light whose energy equals the energy of that transition between those energy levels, right? Think of it as that stair or floor analogy, right? I go up one floor, I go down. How do I go down 2 floors, right? I've got to give up that elevation that I just gained. And so Bohr actually derived how we can calculate the energy of each of those levels, and it works for the hydrogen spectra that we see below. So for the hydrogen spectra, we see 4 different wavelengths of light, 1 in the red region and 3 in the blue and violet region. So he was able to calculate the energy level available for those transitions in giving us principal quantum numbers. Right here are different floors where the electron could be, different energy levels where the electron could be. N equals 1 is the ground state, where ground state is our lowest energy configuration. Anything above that is our excited state. Which is basically an energy level above the ground state. So I've got these certain other energy levels up there, and all of these transitions are associated with a specific wavelength of light that we can observe in the line spectra for hydrogen. And so in this equation, energy equals Planck's constant, which we've already covered, times the speed of light, times Rydberg's constant, which was another constant that was derived to help us understand the line spectra of hydrogen, divided by n squared, where n is our quantum number. And that's what's over here. N equals 1, n equals 2, n equals 3, right? N equals 1, 2, 3, all the way to infinity. So taking a look at Bohr's postulates with respect to the hydrogen atom, right? We have electrons. Electrons are found, right, at specific energy levels. And these electrons are able to move between energy levels. And how does that work, right? When an electron goes from n equals 1 to n equals 3, it must absorb energy. That is equal to that transition. And if, for example, that electron wanted to fall back down, so when an electron falls, from n equals 3 to n equals 1, it must release an equal amount of energy. And so I think one of you asked earlier last week about the photoelectric effect, and you're like, how is that possible? How is that possible that red light doesn't work, but violet light works, right? This is how that's possible. Red light, longer wavelength, lower frequency, lower energy. It does not have enough energy to promote an electron up and out of that energy level that it's sitting in. Whereas blue light has a shorter wavelength, higher frequency, higher energy. It meets that energy threshold. It meets that energy requirement needed to promote that electron up and kick it out of where the ground state configuration where it's located. Right, and so we can calculate that. We can calculate how much energy is released. I can calculate the initial energy. I can calculate the final energy of that electron. More importantly, I can calculate that change in energy that is released or absorbed depending on the transition I'm going, where the important aspects of this calculation, we've already talked about Planck's constant, the speed of light, Rydberg's constant, NF and NI. NF is our final quantum level, and NI would be our initial quantum level. So NF and NI, final quantum level. Right? I need to know where I'm transitioning between and initial. So now we have an equation that helps explain the wavelengths of light that we observe in the hydrogen emission spectra. I can calculate, here are all my possible transitions, n equals 1, n equals 2, n equals 3, 4, 5, 6, 7, 8, all the way through infinity. I can transition between any one of these quantum levels, and I can calculate that energy now, and now I can not only calculate that energy, but I can associate that energy with specific observable wavelengths of light that I see and can observe and record for the hydrogen emission spectra. Right, we're finally tying together that, yes, that wavelength of light's associated with a specific energy, but I can also now calculate specific transitions available to the hydrogen atom that account for those specific wavelengths of light that I'm able to observe. Right, so what does that mean? That means, in this example here, if an electron falls from n equals 3 to n equals 2, so this is higher energy and this is lower energy, right? So for that transition to occur, I'm going to release energy. And let's say that transition occurs and a photon of red light with a wavelength of 648 nanometers is released. So if that transition occurs and an electron goes from n equals 3 to n equals 2, it has to release energy. It's going to release energy as a photon of red light with a wavelength of 648 nanometers. And I just pulled 648, right? It could be any exact wavelength that is in the red spectrum. But what that means is when the electron goes from n equals 3 to n equals 2, it releases a wavelength of light of 648 nanometers. Well, for the opposite to occur, for the electron to go from n equals 2 and be promoted up to n equals 3, for the opposite to occur, what do we need? We need that electron, right? We need to shine a light of 648 nanometer light, right, exactly on that element to promote that electron up to the excited state. So when a red light of this wavelength, right, 648 nanometers, shines on a hydrogen atom in the n equals 2 energy level, right, an electron will absorb that photon of light, absorb the energy from that photon of light, and be promoted from n equals 2 to n equals 3 quantum level. So here's a sample question for you. Calculate the energy of a photon of light emitted from a hydrogen atom when an electron falls from n equals 3 to n equals 1. So the electron is falling. We're going from high energy n equals 3 to a lower energy n equals 1, given that that change in energy equals a negative Planck's constant times the speed of light times Rydberg's constant times 1 over my final quantum level squared minus 1 over my initial quantum level squared. Here are my quantum levels. And to save you the time from calculating the product of Planck's constant times the speed of light times Rydberg's constant, I'll give that to you right there. The negative sign stays out in front. So for this calculation, the change in energy equals a negative 2.18 times 10 to the minus 18 joules times 1 over my final quantum level is n equals 1. 1 over 1 squared, right? A pretty exciting calculation. Minus 1 over 3 squared. So my change in energy for that transition equals negative 2.18 times 10 to the minus 18 joules times 1 minus 1/9. So I do that subtraction and multiply. My change in energy equals negative 1.94 times 10 to the minus 18 joules. And this is important. This is the energy of the electron. So the electron lost this energy. That means that the energy of the photon, so the electron fell from n equals 3 to n equals 1. How did the electron fall down to a lower energy level? It released energy in the form of a photon of light. So the energy of that photon is the positive of that, 1.94 times 10 to the minus 18 joules. Because the electron lost that energy, right, the photon has that energy. That's how the electron lost the energy, releasing that photon of light. So we go through this transition, n equals 3 to n equals 1. I release a photon with an energy of 1.94 times 10 to the minus 18 joules. All right, now here's the good question. Where does that fall in the spectrum, right? What is the wavelength of this photon? So now I know the energy. I know the energy of this photon is 1.94 times 10 to the minus 18 joules. So I can use energy equals Planck's constant times the speed of light divided by wavelength. Ultimately, I'm looking for what's the wavelength of this light. So just rearranging this equation to help me solve for wavelength. Right, I'm going to multiply both sides by wavelength. Wavelength cancels out. I'm going to get wavelength times energy equals Planck's constant times the speed of light. Now I'm going to divide both sides by energy. Energy cancels out. I want to use wavelength equals Planck's constant times the speed of light divided by my energy. So what is the wavelength of light? Well, Planck's constant, 6.626 times 10 to the minus 34 joules times seconds, times the speed of light, which is 3 times 10 to the 8th meters per second, all over the energy that I just found, 1.9 times 10 to the minus 18 joules. So when I multiply and divide, take a look at the units real quick, right? Seconds will cancel out right here, joules will cancel out here. That's good. I'll be left with meters. I'm looking for wavelength. Wavelength is a distance. So wavelength ends up being 1.02 times 10 to the minus 7 meters, or 102 nanometers. And so that's kind of interesting, because if you look for the visible region, right, that doesn't show up in the visible region. There are transitions that occur that exist and release energy. They just happen to release an energy down in the UV region, an energy that we cannot see. So those transitions are occurring, but we cannot see them. The transitions that we do see, right, are of a longer wavelength, lower frequency, of a lower energy. So the transitions we see are actually the smaller transitions, n equals 2 to 3, 3 to 4, 4 to 5 in that region. The larger transitions that are occurring, we cannot see because they release an energy of light that's equivalent to something in the UV region that we cannot detect with our eye. So what's also really interesting about this is the equation to calculate these energy transitions, that came up before they knew these transitions existed that resulted in wavelengths, right, within the region that we cannot detect. So they couldn't see these transitions that were occurring, and yet the equation that was developed also explained these wavelengths of UV light, right, that are given off that we cannot detect, we could not see. So question 6.30 from the homework. Light emitted from one of the following hydrogen atom transitions, n equals 4 to 3, n equals 3 to 2, n equals 2 to 1, causes the photoelectric effect in a metal, whereas light from the other two transitions has no effect. Which transition caused the effect? So what we're looking for is there must be some energy minimum for this process to occur, right? Kicking the electron out of the metal surface. So we're looking for the highest energy transition. So if I look over here, I have n equals 4 to 3, 3 to 2, or 2 to 1. So n equals 4 to 3 is right here. That's a pretty small transition. N equals 3 to 2 is also a pretty small transition. However, n equals 2 to 1 is a very large transition. It's going to release more energy. Because it's going to release more energy, right, it's probably going to be the transition that's initiating the photoelectric effect. So the n equals 2 to n equals 1 transition is the highest energy of the transitions listed. It's probably the one causing the photoelectric effect. Another issue I didn't talk about in this question that's also important to think about, all of these you're releasing energy. All of them I'm going to a lower energy. N equals 4 to 3, 3 to 2, 2 to 1, all of those I'm going down in energy. Had I had a question or had I had an example where one of the choices was n equals 3 going to n equals 5, right, I could immediately eliminate that choice because that's not releasing energy, that's going up in energy, right? This is absorbing energy. So something to think about in further questions that are like this of, is the transition going in the right direction for what I'm looking for? Am I absorbing energy or am I releasing energy?